Ever wonder how your favorite song reaches your car radio or how sunlight warms you from millions of kilometers away? The answer: electromagnetic waves. These invisible messengers of energy are everywhere. Right now, the light from your screen and the signal to your device are both electromagnetic waves. They're a blend of electricity and magnetism, working together to send energy and information across the universe. Most are invisible, but they're as real as the air you breathe. From the warmth of a campfire to the X-rays at the doctor, it's all the same family. When you tune into the radio, use a microwave, or change the TV channel with a remote, you're using different types of electromagnetic waves. In simple terms, an electromagnetic wave is a disturbance in electric and magnetic fields that carries energy. When these fields wiggle together, they create waves that travel incredible distances. It's a silent, invisible symphony that powers our modern world. Have you ever stopped to wonder where electromagnetic waves come from? It's a question that delves into the very fabric of how energy moves through the universe. The answer, surprisingly, all starts with a moving electric charge. Not just any movement, but a very specific kind. When you make a charge accelerate, that is, speed up, slow down, or even change direction, something remarkable happens. It's not enough for the charge to simply move at a constant speed. This acceleration creates ripples, not in water but in the very electric and magnetic fields that surround the charge. These aren't just any ripples, they're disturbances that propagate outwards. Imagine shaking an electron back and forth, a tiny, fundamental particle with an electric charge. As it does, its electric field doesn't just stay put, it moves and undulates, and this moving electric field, in turn, creates a changing magnetic field around it, a field that's constantly expanding and contracting, which then, almost instantaneously, creates another electric field, further out, and so on. It's a self-perpetuating cycle, a cascade of energy. This continuous chain reaction, this interplay between electric and magnetic fields, is what we call an electromagnetic wave, a wave of pure energy, radiating outward in all directions from the source, from that initial wiggling charge. Consider a radio station's antenna, a towering structure humming with activity. Inside, electrons are forced to rush up and down the metal, accelerating constantly, and in doing so, creating the radio waves that carry music and information to your car radio. Your radio's antenna, in turn, picks up these waves, intercepting the energy traveling through space, and cleverly turns them back into the sound you hear through your speakers. The same fundamental principle applies to all electromagnetic waves, regardless of their frequency or wavelength. For example, in a light bulb, hot electrons jiggle and vibrate intensely, creating the light we use to illuminate our homes. And in an X-ray machine, electrons are forced to decelerate rapidly, slamming into a target to produce high-energy X-rays used for medical imaging. So, every time you turn on a light, or listen to the radio, or use your microwave, you're witnessing the result of countless tiny charges wiggling energetically at the atomic level. It's the fundamental link, the underlying mechanism, between motion, electricity, and the electromagnetic waves that permeate and fill our entire universe, carrying energy across vast distances, all from a simple wiggle of an electric charge. That's the magic, the elegant physics, behind every single electromagnetic wave we encounter. Let's look closer at the structure of these waves. An electromagnetic wave is actually two waves, an electric field and a magnetic field traveling together. They're always in sync and always at right angles to each other. Picture your left hand pointing up, electric field, and your right hand pointing sideways, magnetic field. The wave moves forward, perpendicular to both. This three-way 90-degree arrangement lets the wave sustain itself. The changing electric field creates a magnetic field, and vice versa, forming a self-propagating loop. Unlike water or sound waves, electromagnetic waves don't need a medium, they move thanks to their own internal engine. Their oscillations are perpendicular to their direction of travel, making them transverse waves. This is why light can be polarized, as in sunglasses or 3D glasses. It's a beautiful, self-sustaining dance of energy. That's what lets light and other EM waves travel across the universe. The electric-magnetic handshake is what keeps the wave moving. Prepare to have your mind expanded, because here's something truly wild. Electromagnetic waves, the very fabric of light and radio, don't need any physical substance to travel through. They are self-propagating. Unlike sound or water waves, which absolutely need a medium like air or water to ripple and propagate, EM waves possess the remarkable ability to effortlessly move through the complete and utter vacuum of space. Sound, as we know it, is simply a vibration of particles, a mechanical disturbance traveling through matter. But in the vast emptiness of space, where there's virtually no air or matter, sound simply can't travel. It's a silent universe out there. Mechanical waves encompassing both sound and water waves are fundamentally dependent, needing a physical medium to act as a conduit, to carry and transfer their energy from one point to another. EM waves, however, are fundamentally different in their nature and behavior. They're not vibrations of matter, but rather, they are self-sustaining vibrations of electric and magnetic fields, intertwined and propagating together. These fields exist ubiquitously, permeating all of space, even in the most perfect and absolute vacuum imaginable. That's precisely why the life-giving sunlight can travel millions upon millions of kilometers, traversing the seemingly empty space between the sun and our Earth, to finally reach us. Now, imagine for a moment, if light, like sound, needed a medium to propagate, Earth would be an eternally frozen, perpetually dark and utterly desolate wasteland. Therefore, the inherent ability of electromagnetic waves to travel freely through a vacuum is absolutely essential for the existence of life as we know it, and it fundamentally connects us to the vast expanse of the universe. These EM waves zip along at the speed of light, efficiently carrying both energy and vital information across unimaginable cosmic distances. This is the fundamental mechanism by which we are able to see the sun in the sky, the twinkling stars at night, and ultimately, how we receive life-sustaining energy from the depths of space. No medium is required, just the elegant dance of pure electric and magnetic fields in perpetual motion. And that's the underlying secret to their truly remarkable and seemingly limitless cosmic reach. How fast do electromagnetic waves travel? In a vacuum, all EM waves, radio, light, X-rays, move at the same speed, the speed of light, or c. That's about 300,000 kilometers per second, fast enough to circle Earth 7 times in a second. Nothing with mass can go faster. It's the universe's ultimate speed limit. No matter how fast you or the source move, light's speed in a vacuum is always c. This constant speed is a cornerstone of modern physics. But when light travels through materials like water or glass, it slows down. That's why a straw looks bent in a glass of water. Light changes speed and bends, a phenomenon called refraction. The amount light slows depends on the material's index of refraction. The higher the index, the more light slows and bends, but in space, all EM waves cruise at the same top speed. To understand electromagnetic waves, you need to know their language, wavelength, frequency, and amplitude. Wavelength is the distance from one wave crest to the next. Some are kilometers long, others smaller than atoms. Frequency is how many waves pass a point each second, measured in hertz, Hz. High frequency means more waves per second, low frequency means fewer. Amplitude is the wave's height. Higher amplitude means more energy. For light, higher amplitude means brighter. For sound, it means louder. Wavelength and frequency are linked by the speed of light. C equals sign lambda xf. If a wave has a long wavelength, it must have a low frequency, and vice versa. They're two sides of the same coin, defining a wave's energy and character. This relationship shapes everything from radio broadcasts to X-rays. The spectrum of EM waves is defined by these properties. Understanding them unlocks the secret code of light. That's how we read the universe. All electromagnetic waves are traveling electric and magnetic fields. The only difference is their wavelength, frequency, and energy. Scientists organize them into the electromagnetic spectrum, a continuous range from low-energy radio waves to high-energy gamma rays. At the low end are radio waves great for broadcasting and communication. Next are microwaves used for cooking and wireless data. Infrared waves are felt as heat. Night vision goggles and TV remotes use them. Then comes visible light, the tiny slice our eyes can see. Beyond that is ultraviolet, which can cause sunburn. X-rays have even more energy, letting us see inside bodies. Gamma rays at the top are produced by nuclear reactions and cosmic events. Each type blends smoothly into the next, forming a cosmic keyboard of energy. From radio to gamma, it's all the same phenomenon, just different notes. The spectrum is the universe's rainbow of energy. Out of the vast electromagnetic spectrum, our eyes detect only a tiny band, visible light. We evolved to see this range because our sun emits most strongly here. Colors are our brain's way of interpreting different wavelengths of visible light. Red has the longest wavelength, violet the shortest. White light is a mix of all colors. A prism splits it into a rainbow by bending each wavelength differently. Rainbows in the sky work the same way, using water droplets as tiny prisms. The color of an object depends on which wavelengths it reflects or absorbs. A red apple reflects red light, a green leaf reflects green. White objects reflect all wavelengths, black objects absorb them all, making them heat up in sunlight. Our world is painted by the slice of the spectrum we can see. The rest is invisible, but just as real. Electromagnetic waves are the unsung heroes, the invisible threads that weave together the tapestry of modern life. They are the fundamental forces that power our world. They also serve as our window to the universe, allowing us to peer into the deepest reaches of space and time. Every day, without even realizing it, you use them. Turning on lights with the flick of a switch, checking your phone for the latest news or connecting with friends, listening to the radio, enjoying your favorite music or catching up on a podcast, heating food quickly and efficiently in a microwave, or changing the TV channel to unwind after a long day. Our entire communication and entertainment systems, the very fabric of our interconnected world, rely on generating and detecting EM waves, sending information across vast distances in the blink of an eye. In medicine, where precision and insight are paramount, X-rays and MRI scans let us see inside the human body, providing doctors with invaluable diagnostic tools, while focused beams of gamma rays treat cancer, targeting and destroying malignant cells. Ultraviolet light sterilizes equipment, ensuring a safe and sterile environment, killing germs and bacteria with its potent energy, preventing the spread of infection. EM waves also let us explore the cosmos. Telescopes, both ground-based and in space, collect visible light, radio waves, infrared radiation, X-ray and gamma-ray signals, each providing a unique perspective on the universe. From distant stars and galaxies, unlocking the secrets of their formation and evolution. Each part of the spectrum reveals new secrets. Radio waves map the structure of galaxies, revealing the distribution of gas and dust. Infrared light sees through dust clouds to reveal newborn stars and stellar nurseries. X-rays and gamma rays show the most energetic events in the cosmos, like supernova explosions and gamma-ray bursts. From seeing the vibrant colors of a rainbow to enabling global communication networks, EM waves shape our existence in profound and fundamental ways. They carry the sun's life-giving energy, warming our planet and driving our weather patterns, connect our society through instant communication and access to information, and help us unravel the universe's deepest mysteries, pushing the boundaries of human knowledge. Understanding these waves means understanding a fundamental force of nature, a key to unlocking the secrets of the universe. They're the silent messengers, the invisible infrastructure that makes everything we take for granted possible. Science is everywhere, shaping our lives in countless ways. And it's all powered by these invisible waves, the electromagnetic forces that govern our universe.